Today I'm introducing to you and we are going to discuss what we know as the uniform circular motion, UCM. In the uniform circular motion, there are some very interesting things that will come and we learn. One of the things is, of course, even in the motion in one dimensions, when there is no acceleration, the direction is fixed. We say that equal distances are traveled in equal intervals of time. So the same thing exists in the case of uniform circular motion, where equal distances on the circumference of a circle of a given radius are equal distances are traveled in equal intervals of time. So that is a kind of a uniform motion. In uniform motion, because when we talk in terms of the uniform motion in any given direction, then we say that uniformity means that the state of that motion has not to change. In the first law of motion, which you remember, it is defined as every body continues in its state of rest or of uniform motion unless it is impressed by an external force. Now what I can do is, when this law was defined, the state of rest was quite an important thing, but state of rest is a special case of uniform motion where the body does not change its displacement, does not change the displacement. So the velocity in that case is equal to 0. But in the case of or in uniform motion, what they say, that there is a displacement which is taking place. And of course, if I read it like that, the first law of motion of Newton, which is of course not a law which was given or found by Newton, it was found earlier and explained by Galileo, and before that, several centuries before that, the great Arab scientists, they explained it in the same manner as to how this uniform motion takes place. Well, I am saying that equal intervals in equal amounts of time. Now what I do is, I have said here that the surface over which the motion we are going to study is a horizontal surface. So that in this horizontal surface, there is nothing like gravity, etc. that we have to consider, because if there is, even in case of a mass that we have on the body, there is a body which has got a mass, and this is a rigid surface on which the body is placed. Let us see a little bit of deviation, that there is a force of gravity towards the center of the earth, and this we know, we have used it, and this is called the gravitational force towards the center of the body. Now, for this body, there are two equal and opposite forces. So, when we want to press this body, the rigid body, which may be a surface of any kind, then what we get that there is an equal amount of reaction force which takes place here. But I've used the term reaction, and therefore I must clarify to you one more thing, that forces occur in pairs. This is what we often say. But if I have this GM force, where is the pair force of this GM, which is towards the center of the earth? So friends, think, I'll give you just this information, pass on this information and say that it's pair, the counter pair, which is in the opposite direction. It is not this R. It is not this R, but it is an equal amount of force which exists on the center of the earth. So this body on which our earth, Mother Earth, is putting a force equal to GM, this tiny body over here, this small body over here, if this puts an equal amount of force on the center of the earth, there will be occasion to discuss these things later on. Now what we are doing is that on a horizontal surface, I have a rigid body to which we fix a string, an ideal string. So what happens? What happens if we apply a force on this body, this force F, then there develops here another force on the string which is equal to this force and opposite to this force in the opposite direction. This we could do like this also. I can take the string and you can stand in this direction and you pull it, I also pull it, okay. Then the string does not move. What does that mean? That the two forces that are being applied by you and by me, these forces are equal and opposite. The string is in its position as it has been shown over here. Now what arrives is, what we say that this body, which is a string, which could be a spring, an ideal spring also, this body is in a state of tension. A state of attention. A state of attention. What is a tension? Numerically we know that the tension is equal to the force, magnitude of the force, FRF. But let us consider this point P over here. It could be any point between this and this, one end to the other end, because this is an ideal situation, the point can be taken anywhere. Now what will happen? What is the condition of this point? Is it moving? And the answer is no, it is not moving. So we can say that there is a force F from left to right because of this applied force, and there is another force F which is exerted on this point due to the rigid body which exists over here. So tension represents a pair of forces equal and opposite, the magnitude of which we always say that is equal to the magnitude of one of these forces. The direction of the tension is both ways. Okay, so when there is an occasion to see the body like that, we'll talk about it. Right now, what I have a fixed center on a horizontal surface, and tied to it I have a string, and tied to this string, then I have a point at which there is a body, and this body is moving in the anti-clockwise direction, positive direction of motion, like this. So if this point is A, and if I consider this point to be B, at two different intervals of time, okay, then there is an activity, and the activity is that there is an angle theta which is traversed, not traveled, traversed in that time interval, which could be maybe this is the time is equal to t1, this time is t2, etc. So there is interval of time, and that is equal to t2 minus t1, which I can say, and this is equal to the difference of time t. Okay, right now the radius of this circle on the horizontal plane has been taken to be r. Okay, so what is happening is that equal distances are traveled in equal intervals of time. And now let us go back to describe the system. The system here, like I said, my system is this isolated system. We are trying to learn about the things keeping into consideration nothing else but our system. In our system, we say that in a time interval of delta t or t or whatever, okay, if this time I take as equal to 0 and this time as I take as equal to t, then of course what is going to happen, like I have shown over here, the position A and the position B, this is t is equal to 0 and this is t is equal to t, and that angle that elapses, angle that is obtained is equal to theta. So now, like the system, y is proportional to x, then y is equal to a constant times x. This we have discussed in the beginning, right in the second lecture or so, first or second lecture or so. So there is a system, and this system has an angular displacement which is proportional to the time interval, and if so, then theta is equal to omega t. Omega is again a Greek term, okay, and this is small omega and we have capital omega, etc., but here we will take this as a small omega, and this is the constant of the system, yani the constant of the system that we have described, the system that we have defined, and the system is like this, which we have called as uniform circular motion. So theta is equal to omega t, where omega is the constant of the system and is given in radians per second, which is called angular velocity. Now this is angular velocity. Distance is of course moved, but the angle is moved. Okay, like we define velocity as delta x upon delta t, velocity which is instantaneous velocity which is average, etc., etc. So we come back. This is the angular velocity omega t, this system. So see, we defined a very simple system, a system of the kind y is proportional to x and y is equal to kx, where I said that this omega is the constant of the system, our defined system, okay, which is expressed in radian per second and is called the angular velocity. So you can see I have shown this relation, theta is proportional to t, theta is equal to omega t, here in this xy curve, taking t on this side and theta in radians on this side. What we find? We find that like in any other case of y is proportional to x, there will be a linear relationship between the y-axis, the component of the y-axis and the component of the x-axis. And I have just reiterated over here that theta is proportional to t, so that theta is equal to omega t. And if you remember that I said that the slope is d theta upon dt, here it will become equal to omega, because this remains constant and omega does not change with time. So I write it again, omega is equal to, I can say that from this relation I can write omega is equal to theta upon t radians per second. And so in case where if there is equal intervals of time and equal change in the value of theta, if angular variation in a given time is the same as in any other given time, in that case we can say that the average value of omega is equal to the theta 2 in the value that occurs after some time minus theta 1 and divided by the time interval t2 minus t1, like I did in the case of average linear velocity Vx, Vy, Vz, etc. So this will be equal to delta theta upon delta t, which in the limit that delta theta becomes equal to 0 gives us the instantaneous value of the angular velocity d theta over dt. Now next, let's try to understand something more about it. That if we define capital T as the time period of one single complete cycle, complete revolution, then one complete cycle, the total angle is equal to 2 pi radians, because you can see that if this is 4 quarter angles, each quarter angle makes an angle of 90 degrees with each other. So 90 plus 90 plus 90 plus 90, that makes 360 degrees, which is nothing but 2 pi radians. Pi is equal to 180, so this is equal to 2 pi radians, and we complete this. We can start from any point. It's not necessary that we start from here. We can start from here and then come back to here, okay, etc. Now, if in time t new rotations occur, this is again another Greek term, new, with the sound of na, and in English we take it often as n, which connotates the same sound, gives us the same sound, but the Greek sound we have been using and so use. So this is the number of rotations which is taking place. I can say we start from here, in capital T we complete 2 rotations, or in capital T time we have 5 rotations, etc. So now we define that how many rotations, this is the number. Rotations in 1 second, they are equal to 1 divided by, in t seconds, okay. The number of rotations that will take place in 1 second will be equal to nu per second. So t becomes equal to 1 upon nu second, and therefore omega becomes equal to, which was defined as equal to the total angle traveled in this time capital T. I can write omega as equal to 2 pi upon capital T is equal to 2 pi nu radians per second. Now, there is much more to it. I have to define the relation between the displacement vector, the velocity vector, and we will see in the same plane that to this velocity vector we have another vector, which is the acceleration vector which is taking place over here. So all the three things are happening in a plane. The radius is like this, the velocity is always, I have shown here the velocity. The velocity is tangential to the circle at this point, tangential to the circle at this point, tangential to the circle at any point, and anything which is tangential makes an angle of what? It makes an angle of 90 degrees always. So we say that, and we'll see that the velocity is ahead of, is leading the displacement vector. The displacement vector is here by 90 degrees, and we'll also see that the acceleration also leads the velocity vector by 90 degrees, since this is the direction of the displacement. So if I have, you can see, please see when you are going to study it, that the direction of the velocity vector will be like this, which leads this by 90 degrees, and then the acceleration will lead back to it by 90 degrees, so that the acceleration will point towards the center and the displacement will point away from the center, and the two are opposite to each other. Then we get the beautiful relation that the acceleration is proportional to the displacement and is equal to minus something times the displacement, which is the basis of the simple harmonic motion, which is the basis of many other things. So the beauty of this thing is that I have to establish how the velocity and the acceleration, they are related with the displacement vector, which we will come and discuss in the next lecture. Thank you very much for the time being.